In this video, we're going to look at how you find the whole in a rational function. And rational functions have multiple characteristics, and you have values that don't exist. You see that from the domain, you see that from the roots, the intercepts. So we're going to look at the wholes in the function. And the way you find the wholes in the function is you're going to look at the factored form of the function. Again, factored form is going to be your friend in this. Now, there's a difference between a whole and an asymptote. So let's look at the picture here. What a whole is a skipped value not in the domain of the function. It is something that is not in the domain. It is a point that is just skipped over. If you look at the graph, we have asymptotes, and I gave you an example of two asymptotes. I graphed a sample function here. You have an asymptote here, a horizontal one, and a vertical one. Those are lines that the function will approach but never reach. Then you have your whole here. In the whole, you can see the line, the function actually goes straight through the whole. It just skips the point and then keeps going. So there's a difference between a whole and an asymptote. A whole is a single point that the function skips, but then continues on its way. An asymptote is an entire line and set of values that the function will never reach. So let's find the wholes first. Now for the wholes, I was going to use orange, I apologize, but the marker's a little crazy. So let's look at how you find a whole. For wholes, the easy way to find them is you identify identical factors in the numerator and the denominator. So for example, this function that I graphed here was x minus 7 times x plus 1 over, let's see, let me make sure I have the correct equation, x plus 1 times x minus 2. So if I see a function like this, y or f of x, however you want to write it, this is also f of x, function of x. The easy way to identify a whole is you look for identical factors that appear in the numerator and the denominator. In this particular function, we have an x plus 1 and an x plus 1 in the numerator, and we have one in the denominator, which means if I wanted to, I could cancel these out, and I would end up with graphing x minus 7 times x minus 2. However, since the original function has the x plus 1s, you can't just discount them. They're there. So what's going to happen is, because I have a factor and a factor that I can cancel, the function will continue on, and then, because it was x plus 1, you do the same thing. What would make x plus 1 equal to 0? At negative 1, you're going to have a whole. So that is going to create a whole here. When x is negative 1, it's going to create a whole in the function. A whole meaning the function is going to keep going on its way and just skip over that point and keep going. That means this is not an asymptote. It's just a single point, and that's only when you have repeating factors in the top and the bottom. So let's look at another example. Let's say I would have given you this one. Okay. So this is a rational function. How do I identify the wholes? And again, that's f of x equals or y equals. How do I identify the wholes? Well, let's see. Do we have any factors that we can identify that are in the top and the bottom? And we do. The first one is we have an x minus 3 and an x minus 3. That means that we figure out what makes that 0, which is what's going to give us a problem on the bottom. So x is going to equal 3. We've got a whole at 3. Do we have another whole? Yes, we do. We've got x plus 4 and x plus 4. So x plus 4, in order for that to equal 0, x would equal negative 4. So this function is going to have two wholes. One whole at 3, one whole at negative 4. So let's use this information and let's look at our equations here and decide what we have. All right, the first one. Do you have any repeating factors on the top and the bottom? No. So there are no holes in the first one. There's nothing that cancels. Basically, you're looking for something that cancels. If it's in the top, the numerator, and the bottom, the denominator, and you can cancel them out, then it's a hole. Number 2, x plus 6, x minus 6, no other factors. There's no hole here either. There's not a hole here either. We don't have any repeating factors. 3, same thing, 2x plus 5 over x minus 1. There are no holes here. Pretty simple. Number 4, negative 4x plus 2 and negative x plus 1. Now, going back to the factored form, I just realized an error. We could have factored the negative 4x plus 2. I could have factored out a negative 2, and this would have been 2x plus 1 on top. And I should have done that earlier, and that's my fault. So the factored form for this would actually be, I'm going to go ahead and write it over here. If you want to correct this, it's going to be negative 4x plus 2 over negative x plus 1. I could have factored out a 2 or a negative 2. I'm going to factor out a negative 2. And that would have left me with 2x minus 1 on top and negative x plus 1 on the bottom. So that should be your correct factored form for number 4. And I will add that on the video. I'll make sure that that's corrected. So again, though, if you look at the factored form of number 4, I don't have a repeating factor. I don't have a factor that'll cancel. So that again means that there's no hole. Okay. So again, with the error here, it'd be negative 2 times 2x plus 1 over negative x plus 1. I want to correct that and make sure that we have the correct answer. Apologies for that. Negative x plus 1. All right, so let's look at the next one. I have x plus 4 over x times x plus 4. I do have what I'm looking for. I have the repeating factor. So I would set what value would make x plus 4 equal 0, and that is negative 4. You have a hole at x equals negative 4. So this function is going to carry on its way, and it's going to have a hole at negative 4. But what are we supposed to do before we go forward? At negative 4, you can't be in the domain. Well, we've done that with these two, but you know what? It doesn't matter here. That's why negative 4 doesn't work, is because it's a hole. What you're going to see in the hole in the horizontal and vertical asymptotes is that you're going to see some of these values from the domain, because the reason that these values don't work is because they are asymptotes or a hole. So this is okay. That is okay. You can get a value that is not in the domain. That's the whole point of being a hole. All right, so let's look at number 6. Well, once again, I have a repeating factor. I have x plus 1 and x plus 1. So that means I have a hole at negative 1. Because I can't do anything with the x minus 3 because I don't have an x minus 3 on top. I'm looking for repeating factors. All right, let's look at number 7. For number 7, I have an x minus 2 on the top and an x minus 2 on the bottom. So because I have the repeating factor, x minus 2 and x minus 2, that means I have a hole at 2. Because 2 is what would make that x minus 2 0. That's what you're looking for. Because that would wreck the whole denominator and make it 0, and we can't divide by 0, which is why it's a hole. That's why it's not in the domain. For number 8, I have x plus 2 and x plus 2. So that means that my hole is at negative 2. Again, it's only if you have the repeating factor. Up here, we didn't have any holes because we didn't have any repeating factors. Okay? All right. Down here we have x plus 3 and x plus 3. So our hole is going to be at negative 3. And down here, there are not any holes because I don't have any repeating factors. So again, that is how you find the holes in a rational function.